for coming to this talk. It's always kind of worrying when the room is very big that it will end up empty. My name is Nadia. I'm a software engineer in Instagram. I've been with Meta for about over 6 years, and I worked in infrastructure before, so kind of serving all the apps, and now I'm in Instagram product performance. It's what we focus on is the reliability and performance of Instagram, so basically crashes, functional correctness, all that sort of thing, as well as latency, performance, and those things as well. So today I'm going to talk to you about so my smaller team, so these people on the screen now, their names, we kind of focus on trying to automate testing, make testing easier. And we've been so together for a while. We have like an academic background where we worked on research on this subject, and now we're like in Instagram trying to kind of solve the problems that are more practical, but link it to research. So just kind of like overall the testing pyramid. So as you probably all know, we need to have a lot of unit tests. Unit tests will test the smaller parts of the code. I'll talk about, and then so it should be like a pyramid where you have the most unit tests, and then you have a smaller number of integration tests that kind of focus on the kind of the interactions between the small units and how, if they work together, if the APIs have the same definitions, data types, that sort of thing. And then finally, a smaller number of end-to-end tests that kind of test the critical paths through the app and make sure that everything is working. And if you, sometimes the line between unit tests and integration tests is a bit blurry, so sometimes people write tests without mocking all the calls, so then it's kind of like more of an integration test, but at the end, you just want to write tests that test what you want, are not flaky, and are kind of doing the job you want. So it doesn't matter that much. If you think about the costs, of course, unit tests have lower compute costs because they're smaller parts of the code. They don't need emulators. They don't need, especially for apps, they don't need emulators. They don't need to build the app fully. So they're kind of quicker to execute and have lower cost, while on the other end, end-to-end tests require emulators, require creating a user, logging in, all that stuff. So they take longer and they use more compute cost. And if you think also about the effort, it's kind of easier to write unit tests. You're writing this piece of code, you can kind of, you know what you expect from it. You write your unit tests, while end-to-end tests maybe require more effort because you need to understand more about the system overall. And you'd think that in theory you'd have many unit tests, so that's the base of the pyramid, and then you have less integration tests, and finally just a few end-to-end tests that test the critical paths. But in practice, we found that when we looked at the tests, that actually there's people tend to write more end-to-end tests, at least in Instagram, and it does require non-trivial effort because you need to understand a lot of components. Some of them you never worked on. But we also found that unit tests, there isn't a lot of them, and then also they are unexpectedly requiring more human effort than we expected. And the reason is because a lot of these tests take as inputs complex objects that kind of how do you set them up or how do you mock them so that you can perform the test. It's not as easy as in theory we initially thought. So taking that in mind, we kind of see the value of auto-generating these tests so that we can kind of overcome this, not just the fact that the tests are hard to write, but also hard to maintain. If anything changes, then like maybe hundreds of tests start failing, and you have to go and do small changes to all of them. So we see the value in automating. But all different types of tests. So where do we start? And what we started with a few years ago, and I also did like a presentation here in TEQnation about this, was kind of automating end-to-end tests. So we created a tool called Sapiens that simulates a human. It just logs into the app and tries to use different algorithms to cover as much of the app as possible. And what it was trying to find is crashes. So if it crashes, it will, so it runs, if you put up a diff, it will run on the diff. The app is built anyway, because it's a continuous integration system. It will run on this app that was created from your diff. And if it finds any crashes that are new, it will comment on your diff and tell you. And we deployed this for most of the apps in Meta, and we also have this paper talking about the results. And we found that 75% of the crashes we find were fixed by the engineers, so it's kind of doing well. One problem that we faced with that is that we found a lot of crashes, and maybe there wasn't enough time to fix all of them, and it wasn't clear which ones would actually have a huge impact on production and which ones are edge cases that maybe only happen in development or maybe only happen to a very small percentage of. So how do you prioritize which crashes to fix with the limited time for release? So we created this system called Virtual Alpha, which is more a simulation of, so instead of simulating one user, we're simulating a population that we created to kind of reflect production. So we look at production users and see, okay, some have a lot of friends, some have a lot of followers, some have, so there's a distribution of followers, there's a distribution of number of posts, of videos, of photos, all that stuff, and we created a few thousand users that represent that. So they have the same distribution of all these features. And then we run Sapiens on all of them, and then we see the distribution of crashes. So if a crash is spiking, so a lot of users of different profiles are facing it, we think that could happen. That could be more critical for production, so then that's prioritized, or it stops the release, basically. And this was deployed for all of these apps. So Facebook, Messenger, Instagram, WhatsApp, Ads Manager, and Workplace. Okay, so that system was successful. Of course, every journey like this requires a lot of iterations, refinement, whatever. Nothing is completely solved, but we think, okay, what's next? So we thought maybe unit tests, because end-to-end tests are, like we said, very expensive, so we want something that tests on the unit level, that makes it also possible for people to run it locally while they're developing, so that they don't have to wait until they put the diff up to see that something is failing. So why do we want unit tests? First of all, we found in general that unit test coverage is low in our system, so that would be, and it's challenging to increase because of some of the reasons I mentioned, like these, because in apps specifically, sometimes you're passing these huge objects that are holding the state or something, so it's hard to kind of write unit tests for that. Of course, that could reflect that the way the code is written should be changed and be more modular and be more kind of thought out, but we have to work with what we have right now and make sure that nothing leaks to production. So we need to move, our engineers need to move fast with confidence, and if you have a lot of unit tests, you know that the changes you made didn't break anything, and of course, and then that also enables things like refactoring. So things where you know that nothing should change. So you should make your changes, and all the tests, nothing should break. It should be exactly the same. Also, fixing bugs, knowing that you didn't break something else, because this is very common. You fix a bug, but then you broke 3 other things. So it's kind of, and then also maybe enhancing performance without worrying about functionality. So all of these things make us think, okay, let's focus on unit tests. So how would we do that? So the reason the talk is called regression unit tests is because it's very challenging to create unit tests for new code, because you don't know what is supposed to be correct. Like it's based on the design, right? So it's hard to know that someone wrote new code for you to automatically generate tests to say, yes, this is correct. You can maybe find exceptions or something, but you don't know what the requirements are automatically. You can't figure that out. But you can tell the engineer that whatever you did broke something that was pre-existing, right? So regression test. You made your changes, everything that was working before is working, or no, these 3 things broke. Is this intended, or is it a bug? So you show the engineer what failed, and then they decide the tests need to be updated, or no, they made a mistake and they need to fix what they did. So the general idea of what we created is, so we have all these end-to-end tests, and we also have that tool Sapiens. All of them run end-to-end on the system. And we also have developers, when they create something, kind of walking through the app, testing things manually. So if we kind of extracted unit tests from that stuff they're doing, so this is based on the assumption that when we generate the tests, everything is correct. That's maybe not a correct assumption, right? But that's why it's called a regression test. So we generate the tests, you make your change, and then we tell you if your change broke anything that was working before. So the way we did it is we created a Java and Kotlin plugin, so it works for both Java and Kotlin, that instruments the app. So while you're compiling the app, it will add instrumentation. For every method call, it will record all the inputs and the output you're returning, and also for every external call you're doing within that unit, it will record what the value returned was, so that you can mock the object. It will also record other things like the state of the object of the class that you are testing, and like everything basically you need to create a unit test. So we run this instrumenter on the app, and then we create this new APK that is instrumented, and then when the end-to-end tests run, or Sapiens, or anything like that, like developers testing the app, it will just log all of. So every time you call a method, it will log all this information. So this observation logger will log all this information in like a database. And then we have the test generation tool running. It will take these observations and then create unit tests, basically, from these observations. So these unit tests we create, we make sure that they build, we make sure that we run them several times to make sure they're not flaky, they're deterministic, they're not like returning a different value every time, everything is fine, and that they add coverage. So we know that coverage is not the only thing that's important when you create tests, but as a starting point, it's just good to make sure that they add some coverage. So you don't want like 1,000 tests that are testing the same thing. You just kind of want only to keep the ones that cover different paths. Although now we're also just looking at statement coverage, so just to simplify. So once all those tests are created, we put a diff up with the test and put the reviewer as the engineer that wrote the original code that we're trying to create a test for. So, because they would understand the code and they would know if this test is meaningful or like just rubbish, like that isn't testing anything meaningful or something. So, so we deployed this a while ago, maybe 6 months now, but very slowly. We're just trying to. So when you create something like this, the first version is not going to be amazing, or you're just trying to learn and have this feedback loop with the engineers so that they give you feedback, what makes sense, what doesn't make sense, and you adjust the tool to improve that. So we deployed, we landed 518 tests. These numbers mean nothing, so my colleague put them up. It's like how many times it ran. It's just based on how many diffs, or like, because it runs every hour in continuous. But it did block 5,700 diffs, so it did fail on this number of diffs, these tests, and people made changes, and then the tests passed. And so we believe, it's very hard to go and look at every case individually to make sure that, but we believe that it is kind of catching problems. So one thing to mention is that, so we do have assertions based on the return values, to say, oh, is the output the same output you're expecting? But we do kind of put that just as a warning, and the main thing that fails is if you find an exception, basically if the change you made caused an exception to the code. It's just completely failing. But the assertions are kind of, they just need a bit of refinement so you don't get a lot of false positives, because maybe the value, I think you can imagine how just comparing two objects can return some false positives. So we just kind of work on ideas to make it more smarter. So smarter comparing the things that matter and not just comparing every single value in the objects that are returned. There are also some other false positive cases. So in this experiment, because we're getting feedback from the engineers, we did find that there's like a few false positives. For example, it's something that, let's say, can never happen in the way this method is used in our app, but it can happen if you use it differently in the future or something. So although these are valuable still, but because they're not high priority, because that's not how we're using it, so it doesn't matter. So we also looked at, so when we try to release the app, some tasks become launch blocking because we think that these are very critical and would cause an issue. So we looked back, I think over a month, there was 16 launch blocking issues. So we looked at, so kind of back testing. We looked at so the tool, by the way, is called TEQnation. I forgot to mention that. It's very creative. TEQnation, I'm sorry, like, we should have thought a bit longer, but. So we looked back at these 16 launch blocking tasks and found that we could have found 13 of them, stopped 13 of them. The only ones we don't find are, so in this case, so we don't support anonymous objects if they're used in the method call, and also we don't test private methods because you should test them through the public methods. But we just didn't have coverage for that private method, so that was the reason. So you can see that it can be we can overcome this with a bit of like increasing coverage or supporting anonymous objects or something. This is just like a breakdown of the tasks and where they were. And okay, so the challenges we faced, the biggest challenge was scalability, because if you run the app and you log every call, you quickly have like millions and millions of observations, and a lot of them are like the same calls, just with different values or even the same values. So we did some stuff to kind of log only once or something like that. The other thing is that some objects are huge and nested, so it's an object where some of the fields are objects and some of the fields of those are objects, and you kind of are nesting to many, many levels, and then the objects become very huge. So it just becomes a problem with how to save them, because we serialize everything in JSON and then save it. So what we did is kind of like create our own version of JSON to limit the nesting, so it's kind of stop recording after 3 levels or something like that. And that is also one of the causes of the false positives. So for example, you put this object as null so that you can kind of cut the hierarchy down, but then that causes a failure because that shouldn't be null, and then that's a false positive because it wasn't null. So it's not nullable, for example. Also the mocking, you can say, so it's basically, again, even the mocking objects was kind of a scalability issue, because you can have like 100 calls when you call this method, 100 calls within it, and then those have calls, and then there's like just too much to record and too much to put in the test case. So we're thinking about ways to, like we try to use LLMs to simplify and stuff, but also kind of sometimes just make them, just don't mock, just do the call, see what happens. I know that makes them not unit tests anymore, but at the end, it's a process, and we're trying to get to solve these problems one by one. So there's a lot of open problems, basically. Increasing the coverage is another case, because we are relying on end-to-end tests or Sapiens. It's not 100% coverage of everything. Is it important to have 100% coverage? Probably not, but it's important to cover the things that are changed the most or used the most in production or something. So we have to kind of define that better and make sure that we're covering all of that code, and find ways to increase the coverage. So one idea is to use fuzzing, for example. So we record all these test cases, as long as we have a test case for a method, then we can fuzz the input so that we can cover more of the methods, something like that. But then that takes you away. So one of the benefits of observation-based, so this kind of recording from real usage or end-to-end tests or something, is that the tests are realistic, they can happen, they can really happen in the app, because they happen, that's how we save them. So when you do fuzzing, you kind of move again to, so you get the pushback that this could never happen, we don't use it like this or something. So you kind of move away from being realistic test cases that reflect something that can happen. So it's always a balance, kind of where do you stop? And then one important thing that I forgot to mention is readability. Because you're serializing these huge objects, the test case is not as easy to read as if a human wrote it and just, mock this, set this, as it's more readable. So we're also thinking about using different approaches. Again, LLMs seem to be the solution for everything these days, to make it more readable. We also make the debugging, kind of try to make it easy by just kind of pointing exactly at the value, like we show you a diff, basically. This is what the object used to look like. This red thing is now different, and it's now this blue thing, so, or the opposite. So you know exactly what changed. You don't need to understand the whole object. There's actually a paper, I'll show the name at the end, that explains exactly the scalability issues and how we dealt with them and all these other things. So then we had this other project, which is kind of using LLMs to extend human written test cases. So we took the manually written test cases, and we created this system that will take them and then try to test edge cases. So the same unit test, but try to test edge cases, nulls, things, values on the boundary values, all that stuff. So the way it works is, I'm going to go through this very quickly. I actually don't know what the time thing, so it's 22 minutes. When I practiced this, it took 35 minutes, so I don't know what happened. It's kind of probably missed a lot. So what we do is we take tests from our system, and then we pre-process them just kind of to understand what they cover, what they are testing. And then we create these edge cases tests. So we kind of, with the same values, just try to test edge cases. Not the same values, the same test, but different values to test edge cases for every input sort of thing. And then we have, so the reason it's called assured is because we make sure that there's value added. And the way we make sure there's value added is that we build them. So if they, so at each step in those diamonds in the middle, if it doesn't work, then you bin the test. That's it, you don't want it. So we build the test. If it doesn't build, throw it away. And then we run it. If it doesn't pass, we throw it away. Which is maybe not the best decision, but it's good to start with, because if it doesn't pass, then maybe, because it's an edge case, maybe there is something wrong with the system. Maybe they don't check for edge cases properly. But right now, we just, again, we use them as regression tests. So we bin it if it doesn't pass, and then we see if it improves coverage, just so we have a statement about the value added. So if we add a lot of so I personally believe if it tests an edge case, it doesn't have to add coverage. Just, it's fine, just land the test. But just to kind of provide, be sure that it added something, we check the coverage. If it added coverage, if it didn't add any coverage, we bin it. Otherwise, we put it. So we do some post-processing, so basically take the values, create the test, do all the build files and everything, and put it up as a diff, show it to the engineer. So everything we do is we put it up as a diff, show it to the engineer who wrote the original test. So this is an extension on your test, and then they either accept it or reject it. And that's why it's called assured, because it's we know it added, we know it builds, we know it passes, and we know it added coverage. So it added something. So we ran this, we generated 17 tests. I think now it's a lot more, but this is kind of what we, and this is the coverage it added. So It's quite good for 17 tests, and then, especially because you're extending a test that exists, so the easy coverage is already there, because you can write a test that just, the first test you write will cover more than anything else, right? Because it will run the whole class, so. And this is kind of comparing it to human written tests. And here you can see like how we started, so 75 build, then you kind of get how many didn't pass, and I actually don't know why it says rejected 70. It's probably a typo, it doesn't make any sense. Okay, so this is kind of so in conclusion, we found that why not use the end-to-end tests to log these observations, create unit tests from them? Turned out to be, for regression tests, turned out to be useful so far. There's a lot of work to be done to improve it, to make it more valuable, but it's working right now. It's on Instagram, and also Facebook kind of were interested and deployed as well. Some of the other apps are also interested, but we kind of still working with them on making it work for their apps. Because some of the apps are more Java, we are focused more on Kotlin because Instagram is more Kotlin. And I think the thing to keep in mind, like I said before, that this is a first step. It's you probably everyone here has like some why this is a bad idea, but some ideas. But it's true, it's not perfect, but the idea is that, it's not perfect now, but then we take all of this feedback and say, okay, how do we overcome this and this and this? How do we make it more, how do we kind of deal with these challenges? We have to have the first step so that we reach a point where it's really smart and really good and really adding real value. Automated tests, especially this type, doesn't eliminate the need for human tests. So a lot of tests need thinking about the case and what needs to be tested, and there's a lot that is just in the requirements, not in the code. So there's a lot of, if there's a pre-existing bug, this will make sure that the bug is never fixed, right? If people just see, because you created the test based on the buggy version, and then people, when they make a change, they make sure it's still buggy, like the test is still passing. So, but we try to rely on the engineers looking at the test and thinking, no, this doesn't make sense, that it's failing, you should delete the test or something, it should be changed. So there's a lot of reasons why we still need humans to write the tests. It's actually, this is supposed to free up the humans to write the more interesting, the smarter tests, the tests that test the logic deeper. And this is just the first line of defense for any exceptions, any kind of things that are not, because you're working on one part, maybe you don't know that this change would break these other people who are calling the same thing or something. So it's kind of to cover that. It's also important to remember that the ideal way humans write tests is not the way in practice humans write tests. So not every test that is human written is high quality, if that makes sense. Humans are able to write really good tests, but not all tests written by humans are high quality, if that makes sense. So, and this LLM-based thing is kind of showing promising results, and we could kind of try to extend it to not just extend manual tests, maybe extend our tests, that way we get more coverage that auto-generated, and it's kind of promising, as long as you put it in this framework where you can check automatically if what you're adding is adding value or not, so that it becomes scalable. These are the papers I talked about. So each paper talks about, they're all published. You can find them online, because we put them in this archive thing, which is, I think, free. I'm not sure. But also you can email me if you want to read them, if you don't find them. And these cover these different things I talked about today. Go on. Sorry, it's really hard to hear. So we extended human written, so the LLM-based thing is extending human written tests, and then your question is?
If you have legacy code, for example, that doesn't have any unit tests at all, doesn't can the language model handle that? Does it add new additional testing to it, or don't you get any additional tests on that one?
So for the legacy code, we can use the observation-based one. So we did try LLMs as a first step or something, just generate tests, like not extend the test. But it did have, anyone who kind of worked with LLMs, it does start to hallucinate and like write things that are like completely. So we found grounding it on an existing test makes it more likely to produce tests that actually add something and work and compile and pass and all that stuff. But the other approach can be used, the one where we log observations from end-to-end tests, or even using, you can, because the app is instrumented, you can even go in and say, okay, this is my bit of the code, is this kind of 3 screens in the app. I'm just going to click around and use it and let it save observations and then create tests from that. So you can use it for even legacy parts of the code. Go. So when you record the observations, you say, for this class, so it contains all, when we log it, we save all the information we need. So what's the class? What are the values? Serialize it. So we serialize the value, and then we also record what the class was. And even for abstract classes, which kind of implementation was used. So kind of everything you need to recreate the thing is saved in the observation. Yes.
Are parts or more of what you are doing, are you trying to open source them?
Yes. So we actually, we have a plan to open source in this, I don't know which part of the year we are, in the second half of this year. We actually wrote the whole thing trying to minimize dependency on internal code so that we can easily open source. So it's in our plan. I mean, everyone says we'll open source in 6 months. Maybe it will take longer, but the plan is from the beginning to open source within this year, so before the end of this year.
Do you have what name it would probably possibly have, or what name should I try and...
So it's TestGen, the name. Maybe we'll change it, I don't know. But, right, so it's TestGen LLM for the LLM one, and TestGen. Actually, the LLM work we did, because we published it, someone implemented an open source, someone external, we don't know, implemented an open source version of it. I don't know, I didn't look at it, so I don't know if it's really what we did or like their own understanding. But it's out there for if you're interested. Go on.
You started out by saying the unit test took a lot of human effort to fix. Has that become much less effort?
So because these are auto-generated, if the code changes and now they're like, oh, the wrong parameters or the API changed or something, we just have a command. So on your diff, we say, run this command. It will delete the old tests and generate new tests with the new change. So it makes it very easy to maintain. Yeah.
You mentioned about the line coverage. When we saw, for example, in TestGen, it has more coverage if you compare it with human test generated. But I'm curious to know, have you used any mutation testing to make sure that the quality of the tests which created by the TestGen was more or not?
That's a very interesting idea, and we are thinking of that. Actually, one of my colleagues, whose name, so Mark on the first slide, he's determined to do that because it can tell you more about so mutation testing tells you more about the ability to find bugs rather than just coverage, because coverage could be meaningless, right? So yeah, it's on our plans to use that also as a measure of if the tests are good or adding anything. So one run of this thing, I actually don't know where it is right now, but like it depends on the, so let's say I choose a class and say, please generate tests. I don't say please. Generate tests for this class. It should take a few hours, like 2 hours or something. It all depends on, again, you have to instrument the app, build the app. That's where the time goes, right? Building the app, running the end-to-end tests, or that's where so those things take time rather than the generation itself. The generation takes seconds, but because you need to run these things. The way we kind of deal with that is these tests run anyway, so we make a portion of them run on the instrumented app so that we have fresh values every day without having to spend any extra resources or time. A human writing a test, it depends. I mean, I guess, so this is able to generate thousands of tests in a few seconds, which I think a human wouldn't be able to do. But if you compare 1 to 1, or let's say 10 to 10, then maybe it's similar because you spend a bit of time thinking about the first test and then you copy paste and change the values. And so I think it's more as you go scalable, as you do thousands of tests, that the difference is clear. Also, it frees up humans to do more development and more things that require humans than writing these sanity check tests that nothing is breaking, that there are no exceptions. So even if it's a few hours, it still frees them up for a few hours to do something else. But I think the value comes from the scalability. So now, for example, these results were from last half, but the first half of this year is more like deployment, so we're like generating thousands of tests, which would take a lot of human hours if you are generating thousands like this.
Maybe I missed it, but how does the workflow go? So I want to create a new feature, or I want to change something.
Oh, so yeah. So we have annotations. So you write your code and you put an annotation on the methods you want to test or on the whole class and say generate tests. And then we have a continuous system that looks at so every time we build the app, this is kind of running continuously, this process, it will see any new classes or methods that have this annotation and generate tests for them.
Okay, so as a developer, I actively help the system recognize which methods, classes, etc. are.
Yes, so you can. So this is the deployment mode right now. Is you opt in, so you say I want for this method, but eventually it will be like the opposite. You opt out. Don't test this because of some reason or something. Yeah, go on.
In your diagram, you also showed that it doesn't include loop coverage. You looked at the test. What kind of loop coverage are you checking?
So, yeah, right now we're just looking at line coverage. We know it's not the best, but it's just the standard, right? People use statement coverage, so we just kind of we start with that and then see if. I guess if you have 100% line coverage, you can then start thinking about. But it's also always important to remember you don't necessarily need 100% line coverage. Maybe it's more important to focus on the code that is more critical, changes more frequently, causes more bugs, is used in production more, and then because even if it's unit tests, it's still resources and compute time and every test is, even if it's a few milliseconds, it adds up, and then every release is slower because of these tests. So you just kind of have to balance it. Any other questions, or we can? Oh, go on.
With this engineered general sentiment of the tool, did that really free them up the time to run multi tests, or the task of having to review these generate tests kind of defeat the purpose?
So any test you write has to be reviewed. So I don't think it's adding any time in terms of, so it's saving the writing time and then not changing the review time. Of course, you have more tests, so it could let's say you usually review 100 tests a half, now you review 1,000. But there's a way to also kind of move away from having, so once we get more confidence, humans don't need to review, we can, as long as the test pass, do this, do that, then we can kind of just land them. I think it's a bit too early to say. So the general sentiment is, so you have people who are saying, oh, but they can never be as good as humans. Oh, fine, they can never be as good as humans. But humans didn't write all the tests we need. So what do? Wait until humans can write and also, like I said, it's a process. So now they're not so good, maybe in the future. So there's a lot of that, which is fine. There's a lot of kind of criticism that is useful, like, oh, this could cause a false positive because of this. So then we go back to the design and change it so this case doesn't happen, or disable some stuff to... and then there's a lot of people who are very enthusiastic and excited about it and love working with us. There's a lot of initiatives to increase unit tests, code coverage, and that this is working with to make life easier for them. So we could just generate all the tests and then the humans just tweak the assertions or something, or add more assertions or something. So it just makes it easier for them. Cool. Oh, go.
How do you prevent the system from generating the same tests all over again?
Because of the coverage thing. So if it doesn't add any coverage to what we already have, then we don't put the test up for...
Yeah, okay, but it's still generated, but then it discards it.
Yeah. We can, I guess, keep a map of input-output values and then just kind of not generate. The thing that takes the most time is logging the observations rather than generating the test. Because the test is like a template and you just put the values in. So it would be good to not log so that would be very useful and make things much quicker if we don't log the observations we've seen before. So it's very interesting to look into. Cool. So it seems, thank you very much for all the questions. Thank you.